Alright, so we are in the equilibrium section of the Berkeley Review, and we're looking at passage 1. So in passage 1 we are given the following information. We're at 102 Celsius. They give us the partial pressure of carbon monoxide and the partial pressure of O2, and we need to find the partial pressure of CO2. So the relevant reaction is given in reaction 1. So let's go ahead and do the math on this. We know that the Kp is equal to the partial pressure of CO2 quantity squared over the partial pressure of CO quantity squared times the partial pressure of O2. And we know that our Kp is equal to 9. And of course we're solving for the numerator. The partial pressure of CO is 2, and 2 squared will be 4. And the partial pressure of O2 is going to be 1. So that means 36 is the partial pressure of CO2 squared. So the partial pressure of CO2 should be 6 atmospheres. And that's answer choice B. Cool. Alright. Next one. Did you get number 2?
No.
Okay, number 2. Number 2 is a Le Chatelier's principle question. And so let's kind of just scroll back up. Well, actually, let's just write the equation. We have 2CO gas plus O2 gas yields 2CO2 gas. And we're going to add CO2, so we're going to increase the concentration of CO2. Le Chatelier's principle says to offset this, we will favor the formation of reactants. So let's look at these one at a time. A decrease in moles of O2, actually the opposite would happen. Let's eliminate A. A decrease in moles of CO, the opposite would happen. Let's eliminate B. An increase in the value of Kp, only changing the temperature will change the value of Kp, so D is the best answer. No change in the value of Kp.
Okay.
Answer choice D. What's the next one?
4. That. This is the one where I had the right answer
4?
and changed it.
Okay.
One of those.
Well, let's just go ahead and look at it.
Okay.
All right. Oh, no, I just love it when it does this.
Okay.
All right, number 4. Equilibrium constant varies only change in temperature.
Yeah. That's just a.
So the equilibrium, here's the whole reason this happens, and I don't think enough people actually explain this in an introductory chemistry course, so let me do your professor's job for them once again. Should have been used to it by now. So the equilibrium constant is equal to the rate constant of the forward reaction divided by the rate constant of the reverse reaction. Okay. When you change the temperature, you actually increase the rate constant of both the forward reaction and the reverse reaction. But you're going to increase one of them more. In an exothermic reaction, heat is a product, and so the reverse reaction has a greater rate constant than the forward reaction. So if I increase the temperature of exothermic, this will decrease the product ratio. In an endothermic reaction, heat is a reactant, which means Kf has a greater rate constant. So increasing the temperature actually increases the rate constant as a result of increasing the frequency of the collision. So it all comes from kinetic collision theory. And this collision theory was promoted like in the late 1700s, early 1800s. And so it's this fundamental relationship that allows the equilibrium constant to be changed. It's because the rate constants are changed and they're not changed to the same extent. So 4, the answer is D. What's next?
5.
Okay, 5. Let's go back. Okay, a flask is filled with pure CO2. Alright, so here's what we have. We have 2CO plus O2 yields 2 CO2. And I'm going to have 1 atmosphere of pressure. 1 atmosphere of pressure. Now I know that we're going to have some dissociation here. So if we were to imagine, I think the key here is they say the total pressure of the system. So let's imagine that all of this was converted to reactants. It's not. Okay, this will give us an upper limit. If all this is converted to reactants, then I would have 1 atmosphere here and half of an atmosphere here. So the max I can make is 1.5. In actuality, not all of this is going to result in O2 and CO. So it's going to be some amount greater than 1 atmosphere, but some amount less than 1.5. I would choose C as the answer.
Okay. This is the other one I changed. Number 6.
Okay. Number 6. Number 5 is not a trivial question. A lot of people would miss that, I think. Alright, let's go to 6. According to reaction 1, compressing the reaction vessel, which means you're increasing the pressure, right?
Mm-hmm.
So again, and every time I would go back to the balanced equation. I want you to notice I do that every time, and I've been doing this crap for 18 years. Okay. All right, so if I increase the pressure, that is my stress. So always ask yourself the following questions. There's your stress. To offset the stress, you got to do the opposite. I want to reduce the pressure. That means I favor the side of the reaction with the fewest molecules, because in chemistry, pressure is the frequency of collisions of the molecules with the reaction vessel. There are 3 moles of gas in reactants, but only 2 moles in products. That means I will favor the formation of more CO2 until the equilibrium constant is reestablished. So compressing it should lead to an increase in the partial pressure of CO2. I agree. Disagree with B. Disagree with C. Disagree with D. A is the best answer in my opinion. I'm assuming that's what they give us.
And it can't be D because that only changes the temperature?
That only changes with temperature.
Okay.
Because an increase in the pressure doesn't change the rate constant, which is directly related to the equilibrium constant.
Okay.
Most people just memorize that increase in temperature only the only way you can affect an increase in the rate in the equilibrium constant is increase in the temperature. But to know the reason why is very useful. It's because the equilibrium constant is a function of the ratio of the rate constants.
Okay. The last one, I had no idea.
All right. Whoops, I'm missing part of the question, aren't I? Yes, here we go. Okay, so we're going to add calcium hydroxide. That means we're increasing the concentration of a reactant. The Chatelet's principle will shift to the right. So A is not correct. What O2? An increase in the partial pressure of CO. Oh, I see what they're saying now. Oh, I got you.
Describing the calcium hydroxide.
So you've got carbon monoxide plus O2 yields 2 CO2. All right. Now, this calcium hydroxide is going to react with this to produce. So what's going to happen is that this concentration will decrease. So I'm going to get more CO2 and I'm going to get less O2 and less CO. So C is definitely wrong.
Oh, I see. It's removal of.
A is definitely wrong. B is the best answer.
Okay, because it shifts.
Yeah, B is the best answer. That one was really tricky.
It makes sense though when you write it out in a line.
Yeah. All right, so if we look at passage 2, question 8, we have a really familiar system at equilibrium. So the equilibrium constant expression, so we'll go Kp is the pressure of HBr squared over the partial pressure of H2. Since Br2 is a liquid, it doesn't go into equilibrium expression. That's 2.72 squared. However, what I would do is do 2.72 times 2.72 divided by 1.36, because this becomes 2. And so that's going to be 5.44 equals Kp. They're always trying to mess with your head mathematically. You got to beat them at their own game. Yeah, so I'd go D on that one.
Okay. And then 10, the liquid bromine threw me off.
Okay,
I'm trying to
10.
figure that out.
Which of the following starting conditions results in the greatest amount of H2 at equilibrium? Alright, let's move this up just a little bit. Okay, we'll go here. Greatest amount of H2 at equilibrium. It's an interesting question. Other than, we know what the KP is. More bromine should not affect it at all. Let's try a couple of things. So we've got H2 plus Br2 yields 2HBr. If I have 1 atmosphere of this minus 2x plus x plus x I have to be honest, if I were taking the test, I'd pick D. I don't like it. It doesn't feel right, but I don't like the others either. So let's start with what they say the answer is.
Okay, let's say it's B.
They say it's B. I really want to know what the rationale is.
It's
Yes. They say A and C is eliminated. Right. Right. They're identical answers, A and C are, because the bromine is irrelevant. So it comes down to, is it better to have, will you get more H2? See, here you'd have to look at the reverse reaction. And so the reverse reaction here has a Kp of 1 over 5.44. And of course this is going to be 1 minus 2x squared over x. So not very much of this is going to dissociate. Here, so you have 0 and not much dissociates versus 1 atmosphere in B, and the equilibrium constant's 5.44. You still end up with more. I guess reluctantly I would pick B. It's a terrible question, and it's really, I find that hard to believe they would throw that on an MCAT.
okay.
That's pretty demonic right there.
It's a pretty shitty question.
But I'll tell you this, A and C you got to eliminate because they're the same thing, because bromine doesn't matter and they have the same amount of H2.
Yeah, that's what confuses me by that same logic. Wouldn't be in, Anyways, doesn't matter. Okay. So we're almost out of time. The one that I got 11, that was fine.
Cool.
And then 12, I think I got 12. 13 and 14 were really short. I just didn't really know how to figure them out.
13 and 14?
14 especially is just
mixing 3 atmospheres of HBr with 1.5 atmospheres of H2 over Br2 shows which of the following? H2 plus Br2 yields 2HBr. And so initially we have 1.5 atmospheres. Initially we have 3 atmospheres. What's our QSP? Our QSP is going to be 9 over 1.5, which is 6. Our Q is greater than our K. We've made too much product, so we need to go back until this equilibrium, until this 6 becomes 5.44. But I don't need to convert a lot of this to reactant. So this should go up by a little. This should go down by a little. So A's wrong, B's wrong, C's wrong, D's the best.
Yep.
That's a nice question.
And then the graphs on number 14.
Mm-hmm.
I said B and it should be C.
Okay.
What's the distinction there?
The partial pressure. Oh, yeah.
Just the dissociation.
This isn't bad. This
Okay.
isn't bad at all. So initially, let me just erase this. So initially we have only HBr. That means I'm going to produce some hydrogen gas.
Mm-hmm.
So initially it's going to be 0. There's not going to be anything. And then it will slowly increase. Now here's the problem with B. This is a constant slope. That's not true, because the initial amount that's created will be the greatest rate. And then it's slowly going to change its slope until it's 0, at which time it reaches equilibrium.
That makes sense.
Yeah. So C is a better answer choice. What else we got?
Just the last one.
15. Addition of which the following to equilibrium mixture will not affect bromine.
Yeah, that was before I remember that about liquid. So
Yeah. So HBr would, H2 would. Now,
why would
NaOH would neutralize some of the HBr.
Oh, okay.
You have an acid-base reaction, right?
Yep.
B is the best answer.
Okay. Yeah, I think that's the easiest one.
Okay, so I'm going to stop this.